everybody, it's Mrs. Hofferberth. Let's talk about ionic bonding and representing ionic compounds. We're going to start just by reminding you of the properties of ionic compounds. So ionic compounds do not conduct as a solid. They do dissolve, and once they're dissolved, they will conduct electricity then. So they conduct only once they're dissolved in water, forming what we call an aqueous solution. The other thing to know about ionic compounds is although you can dissolve them pretty readily, typically they're really hard to melt. So they're a very high melting point. Let's talk about what's holding together these ionic compounds that give them those properties. So an ionic compound is a crystal lattice of alternating positive and negative charges. If I have something like sodium chloride, then my crystal lattice is a three-dimensional alternating array of sodium ions and chloride ions. So these positive and negative ions are arranged in this three-dimensional structure that's going to maximize the attraction between positive charges and negative charges. Because as we've talked about, opposite charges are attracted to one another. And what makes crystal lattices form an ionic compound different from the metallic ones we already saw is that in the metallic ones, every atom was the same. They were all metal atoms with a positive charge, and it was the electron C that was holding them together. Here instead, I have different ions, positive ions and negative ions, that are arranged in a way that they can attract one another most effectively. Now, we need some new words. The positive ions in this crystal lattice, those are called cations. And the negative ions are called anions. So in my example with sodium chloride, the sodium are the cations and the chloride ions are the negative ions. And where did these positive and negative charges come from? Well, when the sodium atoms and the chlorine atoms came together, the sodium actually gave up one of its electrons and gave it to the chlorine to form that negative charge. So we actually have a transfer of electrons resulting in positive and negative charged atoms and ions that can interact with one another. This gives rise to the properties that we saw. Because in a solid, the positive and negative charges are locked in place because they're attracted to one another, they can't move. Thus, they don't conduct as a solid. But when you dissolve them in water, what you're actually doing is you're separating those particles out and like breaking them up and scattering them throughout the water. Well, once they're separated in the water, now they can move because they can move throughout the water. So that's why they do not conduct as a solid, but they do conduct when they're dissolved. The high melting point we see for the solid compound is because they're really strongly attracted. Think about it. Like if you're a positive cation and there's negative charges all around you, energetically, that's great. It's going to be really hard to separate those ions from one another. If it's really hard to do something, it's going to take a lot of energy. In this case, a lot of heat. And so that's where that really high melting point comes in. I almost forgot one more important property. So one other thing that sets ionic compounds apart from metallic compounds is that the solid is brittle. If you take a salt crystal and you hit it with a hammer, it's not going to bend, it's going to shatter. So let's talk about why ionic compounds are going to be brittle. Okay, back into my picture of NaCl. From a moment ago. So for this, recognize what happens if you try to move the atoms past one another. So let's say I try to move this set of atoms, and I'm going to try to move them all down by one spot. Well, wait a second. If you move these all down by one spot, watch what happens. You end up with positives next to positives and negatives next to negatives. That's terrible. These guys are going to repel and cause the crystal to shatter. So ionic compounds are brittle because they have that very clean, distinct repeating pattern of positive and negative anions and cations in the crystal lattice. And when you try to move the atoms past one another, you disrupt that, resulting in shattering. Make sure that you're comfortable connecting those properties that we talked to back to the bonding arrangements that we have of the atoms, and bring your questions to class. Now, let's say I want you to be able to figure out what the ionic compound that would form when two different elements combine to form an ionic compound. Well, how are you going to know? Okay, so here's the deal. You can actually figure out what kind of an anion or cation will form by looking at the periodic table. In general, metals form cations and nonmetals form anions. Metals will form ions with positive charges, and that's because their outer electrons are relatively far from their nucleus, and there's not very many of them in that outer shell. So for example, if I were to take a look at sodium and look at its orbital filling diagram, it looks like this: 1s2, 2s2, 2p6, 3s1. There is one electron in that outermost valence shell, and so it's going to be relatively easy to remove that electron. And so as a result, when you lose an electron, this goes away, but you keep the same number of protons because it's still sodium, you end up with a positive charge. So your metals, remember you've got your fancy little zigzag line going on down over here, your metals on this side of the periodic table will typically form cations. On the other hand, if we look at something like fluorine and look at its orbital filling diagram, 1s2, 2s2, 2p6. Okay, in this case, if you think about its outer electrons, its valence electrons, that valence shell, the 2s and the 2p, is almost full. You're going to have two options here for forming a compound. You can either remove all of those valence electrons, like we did for sodium, or you can add one more. If you think energetically about what's going to be easier, it's going to be a whole lot easier to add an extra electron to an almost full valence shell. This is further added to the fact that these have, on the left to right spectrum of a period, they have relatively more protons, so you're going to have greater attraction for the nucleus for those outer electrons. And so because of that, your nonmetals will tend to form anions. It's energetically more favorable for them to gain an additional electron or two or three than to lose all of them. And then when you have these positive cations and negative anions, when they come together, there's a huge attraction, and it's very stabilizing. And so as a result, that gain and loss of electrons, that transfer of electrons from anion to cation, is going to be energetically favorable. Okay, so great, you could draw orbital filling diagrams and figure out what the charge is, but there's a quicker way. If you take a look, and you probably should grab your periodic table and get ready to write on the top of your periodic table what these charges are. Everything in group 1, your alkali metals, all of these have one outer valence electron. So they're all going to lose that one electron. Everything in group 1 will end up with a +1 charge. Group 2 is sp2. So they all have two outer electrons, and so they're going to lose both of those from their valence shell. So everything in group 2, all your alkaline earth metals, when you form an ionic compound, will have a charge of +2. We're going to skip the transition metals for right now. Their outer electrons are going into the d orbitals. They're complicated. I'll come back to those in a minute. Jump to where the p block picks up. Everything in group 13 has 3 valence electrons in the outer s and p orbitals. They will be +3. When you get to group 14, it's a wash. They're half filled, and so we would say that these have a charge of ±4. And then once you get to the right-hand side, your orbitals are mostly full. And so you're going to have charges of -3, -2, and -1, respectively, for groups 15, 16, and 17. This is the number of valence electrons needed to fill that outermost shell. Your noble gases, they already have a full shell. They do not form ionic compounds. So metals form cations, nonmetals form anions. An ionic compound is formed by a combination of anions and cations, which means every ionic compound will always be a metal plus a nonmetal for a simple ionic compound. And so you'll always take one positive thing and one negative thing and put them together. Let me show you what kind of compounds we make and talk about what happens when we have different charges. So let's say I have a compound that is calcium and iodine. When I go and look at the periodic table, calcium will have a charge of +2. Iodine will have a charge of -1. That's the number of electrons need to be gained or lost to fill their valence shell or empty their valence shells. Now, when I look at this, and we're going to do a particle visualization where every atom is represented in a little bubble, I say, great, positives and negatives attract. So the calcium and the iodine are going to be attracted to one another as they form a compound. But pause for a second. Do I have an equal number of positives and negatives yet? No. Every ionic compound overall, the total charge has to add up to 0. And so you're going to need to have a second iodide. And so the formula is CaI2. We have two ways to represent what this compound is going to be for this ionic compound. We can do it as a particle visualization. That's the bubbles. Or we can do it in a formula where we're telling someone how many of each ion did we need in order to balance the charge. Let's take a look at 4 more. So I just did calcium and iodine. So we saw that that was CaI2. Let's take a look at potassium and sulfur. Potassium is K+, sulfur has a 2- charge. It's in group 16. And so I look again, I'm like, oh, those don't add up. So in order to have my charges balance out, I'm going to need another potassium to balance the positive and the negative charges. So if I put these guys in bubbles, there's my particle visualization, and my formula tells me I needed 2 potassiums and 1 sulfur. Notice in the formulas you don't write the charges because you can figure that out from the periodic table, so you don't need that. Let's look at aluminum and oxygen. So aluminum has a charge of +3 and oxygen has a charge of -2. Well, I don't have enough negative charge, so I'm going to need to add another oxygen. Shoot, now I don't have enough positive charge. I'll have to add another aluminum. Drat, still now I've got too much positive. I need another negative. Okay, now I'm even. I want you to notice that what I've done here is aluminum had a charge of +2, oxygen had a charge of -2. I had to get to a total positive and total negative charge of 6. I was looking for that least common multiple. And so as a result, my compound for my particle visualization will look something like that with the 2 aluminums and the 3 oxygens. And the formula is Al2O3. The last thing I have is vanadium. I'm going to flash back real quick to the couple slides ago when I had this periodic table and I said we're going to skip the transition metals. Okay, transition metals, these guys in the D block here. These all actually have multiple charges, so you have to be told the charge on these. Most of these elements have more than one possible positive charge. We can talk about that in class as to why that is. So how are we going to tell someone the charge? Right here, if you look at my last example, vanadium and oxygen, this Roman numeral tells me the charge on the metal. So this is vanadium 4. So vanadium has a 4+ charge and oxygen has a 2- charge. It means I'm going to need another oxygen. And my overall formula is VO2, and I drew them too far apart to get a satisfactory particle visualization without redrawing it. So I'm going to redraw them down here. And so that's what we do. You can look at a periodic table to figure out the charge on your ions, and then you look at your anion and your cation, and you use enough of them so that the charges will balance, because every compound must be neutral.